Applications of the theorem of total probability rely upon finding a proper partition of a sample space. Let me start with a historical example which is of some modern significance. What are the chances that the sun will rise tomorrow? Well, this is a perplexing question. There doesn't seem to be much room for chance in this particular game. The problem or this particular question was posed by Pierre-Simon Marquis de Laplace. Today we know him as Laplace, the foremost mathematical physicist of the early 19th century, in his epochal volume, The Analytical Theory of Probability. In this book, he posited the following odds. Laplace was willing to wager about 1.8 million to 1 that the sun would rise tomorrow. And his argument went along the following lines. He said, well, it is manifest that the sun has risen without a break for 5,000 years in a row, or perhaps more precisely by his count, 1,826,213 days in a row without a break. And based upon this number, 1.8 million days of continuous risings of the sun, he was willing to offer odds of about 1.8 million to 1, that the sun would indeed rise tomorrow. A student might well be forgiven for being a little perplexed. What is an underlying model of randomness here? It's not so clear at all, but there are some clues in the way Laplace has phrased his argument. Apparently, Laplace placed significant weight on the fact that there were a succession of a long number of continuous risings of the sun. And this plays into the chance of this event occurring again. Let us detour to set up a different kind of problem where this phenomenon is in evidence. So, as a non sequitur, a break from the direct line, let us go back to a ball and urn model. Consider, as I've shown in the picture, a system of 11 urns, each containing 10 balls. Let us say we number the urns 0, 1, 2, 3 up till 10. The balls in each urn are of two types, red and black. The urn at the left consists of all the balls which are black. The urn at the right consists of 10 red balls. And generally, say the kth urn in the middle contains k red balls and 10 minus k black balls. Here's a setting. Now let's quickly abstract this, and instead of restricting ourselves to 10 balls, think of a large number, say n of balls and n plus 1 urns. So we are given n plus 1 urns labeled 0 through n. Each urn contains n balls. The kth urn contains k red balls and n minus k black balls. The chance experiment proceeds as follows. One of these urns is selected at random. Having picked an urn, we set it aside and repeatedly sample balls from it randomly and with replacement. Our question: suppose we are not told which urn was selected, but we are told, this is side information, that our successive draws resulted in R red balls in a row. What is the chance that the R plus 1th draw from that selected urn will result in a red ball? The tenuous connections to the Laplacian problem are clear. There is a repeated occurrence of an event, and we now ask, how does this condition a future occurrence? But in this setting, a chance experiment is easy to construct and the underlying sample space is easy to identify. So without further ado, what is the sample space? Well, all the elements that are uncertain in the experiment can be categorized as follows. First, there is a selection of an urn. Next, there is a repeated selection of a ball with replacement from that urn, each ball characterized by its color, red or black. Since we are considering a selection of an urn and r plus 1 selections of balls, we could think of the sample space as a string, a sequence of letters, a specification of an urn, say x, taking values from 0, 1 through n, followed by a specification of ball colors y1, y2, y3 through y sub r plus 1, where each value y takes one of two colors, red or black. Now we have an understanding of what constitutes an idealized outcome of this chance experiment. What are the events of interest? Well, let's begin. Naturally, one event of interest is the event that r draws from that selected urn result in r successive red balls. A second event of interest is that r plus 1 successive draws from that selected urn result in r plus 1 red balls. Let's introduce some notation. Right. Let h sub k denote the event that the first k draws from the selected urn result in red balls. Formally, this is the collection of sequences x, y1, y2 through yr plus 1, where y1 through yk are red and the other variables are free to move willy-nilly as you will. Of course, the particular values of k of interest to us are k is equal to r and k is equal to r plus 1. Now, this by itself is a complex-looking problem. There are too many moving pieces here. We naturally look about for a way to partition it, break it up into simple, homogeneous segments. And a natural partition is immediately suggested by our notation by the first element in the sample point, the selection of the urn. So let's introduce some ancillary notation. Let A0, A1, A2 through A sub n represent sequentially the events that the 0th urn was selected, the first urn was selected, and the nth urn was selected. Generically, let A sub j denote the event that the jth urn was selected. J runs from 0 through n. Naturally enough, we are going to condition on these events A sub j as ancillary events. Observe that since some urn has to be selected, the events A0, A1 through An partition the sample space. All sample points have to be in one or the other of these events. And it's manifestly clear that these events are disjoint. They are mutually exclusive. If one chooses, say, the third urn, then one manifestly has not selected, say, the 7th urn. We are now left with the task of specifying a probability measure. And in such settings, it is most natural to specify the measure implicitly via conditional probabilities. Let us start with the ancillary events A sub j. In the Laplacian model, there is no reason to believe that any one urn is more likely to be selected than any other, and therefore we assign to each of these events A0, A1 through An equal probability 1 over n plus 1. Having selected an urn, what can we say about the events h sub k? That k successive draws resulted in red balls. Now, if the jth urn was selected, then we recall that the jth urn contains j red balls and n minus j black balls. Each draw of a red ball has got j possibilities. K successive draws, the number of possibilities in total is n to the power k, And the number of ways of which these n to the k can result in red balls is j to the k. Remember, the urn contains j red balls. And therefore, if you're looking at a string of k draws, we have j, 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 k times, and by the usual principle of enumeration, there are j to the power k ways of selecting k red balls from the Z. Now, the probability, therefore, that given that the jth urn has been selected, that k red balls in succession have been drawn is j to the power k divided by n to the power k. Here's a beautiful and simple prescription of an implicit probability measure. Just as we did in the case of two dice, we can now go back and figure out the mass function attached to each particular idealized outcome. But that will take us a little far afield, and it is not necessary for our purposes.